So why do materials heat up to different temperatures, even when exposed to the same energy? Sand is a solid. Its internal structure is relatively rigid. When energy hits it, that energy has nowhere to go except straight into raising the temperature. It heats up fast, aggressively. That's why it burns your feet. Water is completely different. Water molecules are held together by hydrogen bonds. These bonds can stretch, rotate, and absorb energy without immediately raising the temperature. Water acts like a giant thermal sponge, soaking up energy before its temperature even starts to climb. This difference is captured by one number: the specific heat capacity. Its definition is simple: the energy required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. Let's take an example below. We have 1 kilogram of sand and water. How much energy would be needed to raise their temperature by 1 degree Celsius? As we apply heat energy, the sand required just 830 joules. However, the water took a lot longer, needing 4,180 joules. So water absorbs 5 times more energy than sand for the same temperature rise. That is why engineers choose water as a coolant in almost every major industrial application. Engineers use a simple but powerful relationship to connect energy, mass, specific heat capacity, and temperature change. Q equals m Cp delta T. Let's break down every term. Q is the heat transferred, measured in joules for a fixed mass, or kilowatts for a continuous flow process. This is what you're solving for, the heat duty your system needs to deliver. M is the mass. For a batch process, it's measured in kilograms of material. For a continuous process, it's known as the mass flow rate measured in kilograms per second. Cp is the specific heat capacity, the property we just discussed. The thermal sponge rating of your fluid, measured in joules per kilogram per degree Celsius. And delta T is the temperature change, which is the difference between the outlet and inlet temperature. This single equation is very powerful as it determines the size of your heat exchanger and your entire energy balance for a process stream. Let me show you exactly how to use it. Imagine you are a process engineer. You need to heat a water stream from 20 degrees Celsius to 80 degrees Celsius. Your mass flow rate is 2 kilograms per second. How much heat duty does your heat exchanger need to deliver? Step 1. Calculate the temperature difference, which is 60 degrees Celsius. Step 2. Substitute everything into the heat capacity equation. This gives you a heat duty of 501,600 watts, or approximately 502 kilowatts. That is the heat duty your heat exchanger must deliver to raise this water stream from 20 to 80 degrees Celsius. Let's take another example where we cool a glycol stream. Glycol is commonly used in refrigeration systems and as an antifreeze in applications where water would freeze or cause corrosion. Step 1. Calculate the temperature difference, which is 50 degrees Celsius. For cooling duty, we take the inlet temperature minus the outlet temperature, so our heat duty remains a positive number representing heat removed. Step 2. Substitute everything into the heat capacity equation. This gives you a cooling duty of 180,000 watts, or approximately 180 kilowatts. This huge difference is entirely because glycol's specific heat capacity is 2,400, which is significantly lower than water's 4,180. This is exactly why the choice of heat transfer fluid matters so much in process design. Now 3 mistakes I see regularly with this equation. The first mistake is units. Heat capacity can be in joules per kilogram per degree Celsius or kilojoules per kilogram per degree Celsius. If you're using joules per kilogram per degree Celsius, your heat duty will be in joules or watts. If you're using kilojoules per kilogram per degree Celsius, your heat duty will be in kilojoules or kilowatts. For a batch process, mass is given in kilograms and Q comes out in joules. For a continuous process, mass is given in kilograms per second and denoted by the letter M with a dot on it. Q comes out in joules per second. Mass flow rate should always be in kilogram per second. However, if given in kilogram per hour, you must divide by 3600 to convert it. The heat equation only works for fluids which stay in the same phase. If the gas or liquid begins to condense or boil, the equation is no longer valid. Why? as the temperature does not rise during a phase change. If you enjoyed this video, please remember to like, comment and subscribe.